Hello, everyone. The following is the second in a series of two lectures covering chapter 42. Today, we'll be talking about Bohr's model of the hydrogen atom. This entire section is talking about a now outdated model that, while successful at the time in explaining the main emission and absorption lines for the hydrogen, nowadays it's been fully replaced by the quantum mechanical model of the atom that actually explains everything that's now been observed and understood about hydrogen and other elements. Still, it did get some things right, and it was a stepping stone to the quantum mechanical model we have now, which is why we are studying Bohr's model for today. In about 1913, Bohr published his theory of the hydrogen model, that, unlike Rutherford's model, could actually explain the emission lines and didn't have the issue of electrons orbiting and therefore eventually crashing into the nucleus. And it borrowed ideas from all parts of physics. The notion of sort of orbiting electrons was still there, but incorporated Einstein's idea of photons plus Planck's idea of quantum theory and quantized energy, and even some Newtonian mechanics, if you consider stuff related to angular momentum for the electrons. And with that in mind, let's talk about the action model itself. It's based on four main postulates, and again, it's talking about the hydrogen atom. So everything we'll talk about for this model is a system of one proton forming a nucleus and an electron within the space of the atom orbiting around it. Postulate number one, which is borrowing from Rutherford's own planetary model, is that the electron does orbit the proton in the center, the nucleus, in an orbit maintained by the electrostatic force. The second postulate states that only certain orbits are allowed. These are the stationary states of the system, and in these orbits, the electrons are not radiating any energy, and instead the total energy of the system remains constant while in the state. The actual motion of the electrons around the nucleus can be described with classical mechanics, just orbital motion like planets around the sun. Thirdly, and this is when we start getting to the idea of quantization, is that as electrons in the hydrogen atom transition to a lower energy state, they emit energy in the form of electromagnetic radiation. The amount of energy emitted depends on the energy difference between the level it's jumping down to and the level it jumped from. That difference will tell you then the energy of the photon emitted, which is a product of Planck's constant and the photon's frequency. This process of the electron transitioning to a different stationary state around the nucleus was not something that could be derived with classical mechanics. This transition could not be explained. It wasn't like a physical kinematic transition. It was something else entirely. Also, photons can be absorbed provided that they have the exact energy to allow the electron in the system to jump to a higher energy state. When the photon is absorbed, it's dissipated entirely, and the atom reaches a higher state, so the electron would be in a different orbit. Lastly, the fourth postulate states that the angular momentum of the orbiting electron is quantized. That means that the angular momentum of the electron can only have certain values. And this is based on the momentum only having a value that's a multiple of h bar. And that leads to the formula shown here, which tells you the angular momentum written as the mass of the electron times the speed of its orbit times the radius, the radial distance from the electron to the nucleus, r, must equal some integer n times h bar. This quantization of the angular momentum, if you look at the total energy of the hydrogen atom based on the speed of the electron and the electric potential energy between the nucleus and the electron, you can see that with this quantization condition in place, it also leads to the radius of orbit being quantized and also the total energy of the system. Furthermore, the lowest possible orbital radius is what's called a Bohr radius and corresponds to the ground state. So basically, the ground state is the lowest possible energy state for the hydrogen atom, and that's a point in which the electron has an orbit whose radius is equal to what's now called the Bohr radius, which is about 5% of a nanometer. For any higher energy state than the ground state, the radius of orbit is just um, the state number squared times the Bohr radius. So the second state has a radius that's 4 times the Bohr radius. A third state has one that's 9 times, and so on. The quantization of radius and that came from the quantization of angular momentum also leads to the energy of the system of the whole hydrogen atom to being quantized as well. So for any state, n, there is a certain energy level associated with it, and thus the hydrogen atom can only have energies that satisfy the equation shown below. And on the graph on the right here, we see the different energy states and the different radius as energy increases. So n equals 1 represents the ground state, the lowest energy level possible. That has an energy of about negative 13 electron volts. The next one has an energy of negative 3 electron volts, and so on. So note two things: that as you go up in levels, because n is in the denominator, the levels become a smaller negative number. In other words, you start from negative 13, in the second level you up to negative 3, and then you keep approaching a energy of 0 from a negative number. That means that all the energies are negative, and it increases towards 0 as the level increases and increases. The reason why the ground energy is negative and you work your way towards 0 is because by convention, a electron that's not bound to an atom is considered to have 0 energy. So in the hydrogen atom, where an electron is bound to an atom, it must therefore have less than 0 energy because it's bound to the atom. So like I said, the energy of any level is inversely proportional to the level number squared. And that also means that as you go up and up towards higher levels, the differences in energy between higher levels is smaller than the difference between the lower levels. So you can see how on the graph on the right, level 1, 2, and 3 are fairly far apart, but 4 and 5 are a lot closer together. If you recall the particle in a box wave function from chapter 41, you may have noticed that the energies of the particle in the box, their separation gets bigger and bigger as you go up in level. And that's because the energy of the particle in the box is proportional to the quantum number squared. So if the atom receives enough energy that it can jump out of the ground state to an energy of 0 or above, Then the electron becomes unbound. It is freed from the nucleus, and thus the atom just becomes a nucleus. We say it is ionized. It has lost an electron. So the ionization energy is just the least amount of energy required to ionize an atom from its ground state. In the case of hydrogen, it's the energy of the ground state, positive, 13.6 electron volts. So at the ground state, the energy of the hydrogen atom is at negative 13. So if it receives that much energy, it'll bring the total energy to zero, and the electron will be freed. This is something that the Bohr model got right. The electrons does have a energy binding energy of 13.6. So I think that will separate it from the proton. And while we're at it, so we already established a formula to calculate the quantized energies. We can then calculate the quantized frequencies and wavelengths that are emitted when an electron in the hydrogen atom jumps down to a lower energy state. So this predicts and explains why the absorption and emission lines for hydrogen were discrete, because they occur when the electron in the hydrogen atom either jumps down a few levels to and then emits a photon, or it absorbs a photon and jumps to a higher level. So for the formula shown here, you can then find the wavelength of the photon emitted when you jump from some initial state Ni to some final state Nf. The formula at the top is written in terms of the frequency of the photon emitted, but then it can be rewritten in terms of the wavelength. Note this is the Rydberg constant shown in section 42.1. So this is the same formula used to describe the wavelengths of the Balmer and other series, and this is just a more general formula. So what the Bohr model does is it tells you that, all these series seen, they were representing the energy radiated by the atom in the form of photons when they move to a particular final state. So the Balmer series, for example, were the wavelengths of light seen when electrons in the hydrogen atom jump down to the second state from upper ones. The Lyman series are when electrons jump down to the ground state. Bohr took this model, which seemed to work fairly well at the time for the hydrogen atom, the most simplest atom you can think of, one electron, one proton, and had moderate success applying it to highly ionized elements. These were elements that had just a single proton left in their orbit. And it is true that you will find in hot gases like stars, highly ionized gases. So you do find these gases like lithium or beryllium that have everything but one electron left. And what he did was he developed a model for the possible energy levels of an ionized element. So he took the formula for the energy and radius of the hydrogen atom and generalized that to any atom as a function of not just the energy state n, but the atomic number of the element. So atomic number is just how many protons are in the nucleus. So he developed Bohr radius for any element and also the quantized energy. So this works as long as you know the atomic number of the element, and also that it's an ion, so that there's only one electron around the nucleus. However, the model does not properly cannot describe complex atoms and elements that have more than one electron. So yeah, Bohr's model effectively combined a lot of classical physics with more up-and-coming ideas. He took Rutherford's orbital model, and that's postulate 1 follows that main idea. But postulate 2 talks about certain ground states that are possible, certain stable states, which is based on Planck's theory of quantized energy that Planck used to explain black body radiation. And then he took Einstein's idea of the photon to explain that electrons could become excited and jump up a level if they absorbed energy, or they could jump down to a lower energy level and release photons. And finally, the idea of having orbital angular momentum by virtue of electrons orbiting a proton is something that you can model with classical mechanics. But of course, the idea that this orbital angular momentums were quantized, you couldn't have any particular one. You had to have certain discrete momenta, certain discrete radii, is again following Planck's idea of quantization. So he did predict the ground state energy of hydrogen, and the absorption and emission lines that were seen at the time were also predicted by Bohr's model. But later on, it was found that the emission lines actually could be further divided. They had like a, if you had a better resolution in your spectrometer, you see that some of the lines were like three little lines kind of close together. So there were more complex effects happening in the emission of hydrogen and other atoms that couldn't be explained with Bohr's model. And also, we now know that electrons exist not in orbit around the nucleus, but in a probabilistic cloud around the nucleus. And you can find the electron basically anywhere in the look in the nucleus around the nucleus. Some areas are more likely than others. It is true that an electron is more likely to be found at a distance equal to the Bohr radius, but it can still exist anywhere else. Um, and this, contributes part of the quantum mechanics model, but that is beyond this course. So that's all we'll say about the model of hydrogen. You may remember how when we established special relativity, we showed that when things start moving near the speed of light, classical mechanics cannot describe them properly. But if things are moving slow, then classical mechanics still works. For the case of quantum mechanics, we may ask a question: when can we use classical mechanics? When does quantum mechanics become so macroscopic that classical mechanics takes over? Well, once you have very high quantum levels, so like say n is greater than 1,000 or so, then even the hydrogen atom can be modeled with classical physics. Because at really, really high energy levels, the separation between the energy states is so small that it's almost continuous. And at that point, the radiation that an electron emits at high energy levels can actually be modeled as having the same frequency as the electron's own revolution. So remember that the photons emitted have their own frequency, but at high energy levels, the frequency of those photons matches the frequency of the electron's orbit. But again, only for high levels. And that's why in the real world, everything is in quantum states of very, very high level. So energy, everything that's normally seen as discrete values in the microscopic world, in the microscopic world, the energy separation between each level is so small that everything seems continuous rather than quantized. Thus, we go to state the Bohr's correspondence principle and summarize that idea that quantum physics agrees well with classical physics when the difference between quantized levels becomes vanishingly small. Okay, so this quick quiz asks about a photon coming near the hydrogen atom with an energy of 10.5 electron volts. What happens? So the energy that a hydrogen atom will absorb has to be discrete, has to be the right amount to get it to go up to a certain level, or it has to be more than its ionization energy. So with 10.5, if we look at the rungs of hydrogen, with 10.5, you're in the ground state. With 10.5, that would get you somewhere between states. So it can't do anything with that. It needs to either get enough energy to get to the right state, or it needs to go above zero. It needs to go above the ionization energy. So with 10 electron volts, it's not enough. It corresponds to a quantum level of 4.39, so it doesn't get you anywhere. And this question compares two transitions, the hydrogen atoms transitioning from the n equals 3 level to the n equals 2 level, and compare that to a transition from the n2 level to the n1 level, which transition results in the emission of a longer wavelength photon. So the emission with the longest wavelength is the transition that has the smallest gap in energy. As you jump down a level, you will emit a photon with energy equal to the difference between the levels. So recall that as you go towards the ground state, the gaps become bigger. So the energy gap between level 1 and 2 is bigger than the gap between level 3 and 2. So in other words, when you jump from level 2 to 1, the gap is bigger. So you will release a higher frequency photon, therefore shorter wavelength than when you jump from 3 to 2. So the first transition has a longer wavelength photon because it's the lowest energy. And then in the example here, you're asked to find the wavelength and frequency of the photon as it jumps from the first excited state to the ground level. And here you see the energy is 122 nanometers, so nearly it's ultraviolet. Then the frequency, you can find that using the wave formula. And you find the energy of transition from the fifth level to the first. And you can also use the formula n squared times the Bohr radius to find the radius at any level. And then using the Bohr's model, they can also calculate the electron speed using the once you know what the level is. Or you don't need to know the level, you can actually calculate the electron speed. If you already know the radius of the electron, you can find the... If you already know the radius of the electron at that particular level, then you can calculate the speed of the electron using the formula below. As you can see, it's pretty fast. Not relativistic, but still fast. Now, this part asks you to treat the radiation classically, which means that the radiation emitted by the electron is just a classical wave. So whatever frequency the electron has of orbit is the same frequency of the wave emitted. In that case, you can find the frequency of orbit if you just take the formula here, speed over 2 pi r gives you the frequency of rotational orbit. You might remember this from circular mechanics. And then this is the frequency. It's really fast, 5 times 10 to the 13 hertz. And whatever energy radiates as a wave, because it's a classical model, has the same frequency. So then the wave that it radiates is this much in frequency, and thus you can calculate the wavelength of the wave again using the wave formula. In this case, look, the wave is actually bigger than what the Bohr model predicts. And here's just kind of like a breakdown. So according to the Bohr model, the wave is a wavelength of 95 nanometers, while using a classical model, it's much bigger than that. It's a micrometer, so it's about 100 times bigger. So to give a good result, the Bohr model does give you a good a result that agrees with experimental findings. You can't use a classical model because, as you can see, the wavelength is way too big. If the n, if the level was like above 1,000, then the classical model would give a good prediction for the wavelength. But in this case, it doesn't. As you can see, the difference between the classical and the Bohr prediction of the wavelength is a lot bigger. So you want to use the Bohr model in this case. Anyways, that's all for chapter 42. I hope you join me next time where we will discuss the last and final chapter, 44. Thank you and have a good day.